see any more questions, so I'll just plug ahead if that's okay with you. And what we just saw was the electrical potential energy is proportional to the charge. We're talking about electrostatic forces. We're not talking about gravitational forces. Sorry about that. The electrostatic potential energy is proportional to the charge. And what is weird here is we're going to if we investigate the proportionality factor. We've done this a couple times in previous laws and previous investigations, that if we find a proportionality, then we just go and we measure it, and we can find out what that proportionality factor is. In this branch of physics, that proportionality factor it's not a property of the charge that you've placed in this region where there's a separation of charge, right? It has nothing to do with the charge itself. It has everything to do with the location in space that it has been dropped down into, this region in between those two plates. And what we do is that proportionality factor we call the potential V. I'll use this capital V with little weird lines on the top just because V pops up a lot in other contexts. So I'm trying to discriminate that I'll always use this capital V here. So so this is our definition. The electrical potential energy is equal to the charge times the potential at that region of space. And note that just like in gravitational potential energy, if you go back and you think about this, the actual value, the numerical value of what the gravitational potential energy is, the number, never ever really mattered. It was always differences, right? It was always differences. And please do review that if that is a mystery to you. It's a big deal with potential energy. The number, the actual physical number at any particular point in space, can be chosen to be a convenient number, in the sense that you can set the zero of your scale anywhere. So if I'm pointing to, can I point over to Mega Man without losing my finger? I can't. Somehow my hand disappears. So, on this building here, the easiest thing for me to do is say that the gravitational potential energy is 0 at the floor of this building, and it's some other number at the top. Because then when the ball falls off the building and lands on the ground, I say it has 0 when y equals 0, right? It's a choice. As long as we stick with the convention that we choose, that's fine. But it's an arbitrary choice, and the same thing's going to happen with electrostatic potential. So long story short, I'm being a little bit verbose this morning. Only changes in potential energy are significant. So all we care about are changes in potential, differences in potential. You can choose the 0 of this scale of potential at any convenient place. Right, so when I'm, to skip forward a bit, when we start talking about batteries, if I talk about a battery and it has 9-volt potential difference between the two terminals, it could be that, one of the terminals is at 0, one is at 9. It could be that one of the terminals is at 10, the other is at 19. It could be one of the terminals is at 100 volts, the other is at 109 volts. All that matters is the difference between 2 points in space. And that may seem weird, but I really want to stress that and allow you to please ask questions if that does puzzle you. We'll see some examples of this as we go. So now we talked a lot about gravitational potential energy during this lecture, probably more about gravitational potential energy than electrical so far, because I like the analogy. It seems like it's very close. In my mind, it seems very similar. And I have a good grasp in my mind about what's going on with gravitational potential energy. So I want to torture this analogy to death. So on the left, I have gravitational potential energy. I remind you that the formula for it is U equals mgy. And the m, the mass, is something that the particle is born with. If this is, or the object has some intrinsic quality called mass that is not going to change as long as you don't damage or change the object in some fundamental way. It's a property, a fundamental property of the particle. And the rest of it is some characteristic of the location of that particle in space, right? G is a characteristic of how strong the gravitational force itself is, and Y is just the location of that particle. My tortured analogy here is, if we look at electrical potential energy, we have U equals Q times V. The Q is a property of the particle. Unless you do something dramatic to change this particle, it's an intrinsic property, a characteristic of this that kind of characterizes its nature. It's a property of the particle, of the object that you're talking about. And the potential, this big V, is a characteristic of the location. So you know, I'm trying to build this up by steps with our familiarity with gravitational potential energy. So let's see if this helps at all. I'll pause for a moment here. Do we have any questions from the audience?
Yeah, I do have a quick question. What is the way to calculate the potential, or not the potential, the proportion?
What is the? Oh, okay. So the way that there's a very nice example of this in your book, which I'll summarize in 30 seconds here. But the basic idea is, if I have a region in space where there is, you know, some separation of charge, what would happen is I would measure the work that it took to take, you know, a 1 coulomb charge to move it from here to there, and then I could measure the work that it takes to move a 10 coulomb charge from here to there, and a 100 coulomb charge from here to there. And in each of those cases, I could measure the work, and that work is in magnitude is exactly equal to the change in potential energy. So from that, you know, I can measure 3 or 4 different places where I could measure the change in potential energy, and I would get that proportionality factor. And in each of those cases, so here, if I had a 1 coulomb charge and I moved it from here to there, and measured the proportionality between the work that I did and the charge, and then I did a different charge, 10 coulombs, and I got a different amount of work that it took me to move it from here to there, the proportionality would be the same in both of those cases, and that number is going to be the potential.
Okay, thank you.
Okay, Brendan. It is, you know, this is spelled out a little bit more elegantly than I'm saying it verbally in your text. If you give me 1 second here, but that's basically the idea. You'd want to examine a region of space with several different charges, and if you're using the most recent version of the book, it's in section 21.1 on page 736. Charged particle potential energy is proportional to its charge. So I hope that helps. Just my short analogy here, and there's a much longer explanation in the textbook. All right, so I think we just did this. Okay, so now kind of looping around back to where we started, I said that hopefully this is something that we're familiar with. Potential is measured in volts. And I want to do like a numerical example here that's kind of the analogy of dropping the water balloon off of Demerit Hall. So we have here a 10-volt battery. What this is doing is creating some potential difference between 2 regions of space. I've hooked it up to a parallel plate capacitor. So I have some array of positive charges up here, some array of negative charges down here. I'm allowed to set the scale wherever I want. So I set the 0 of my scale here. As long as there's a 10-volt difference between these two, I'm okay. I could have called this 100 and I could have called this 110. I don't want to confuse you with this, but there's nothing magical about where I set the 0, as long as I honor the difference between the two and set it equal to 10 volts. So I set this region up in space where I have a potential difference. I let go a positive charge. Because I like protons, I'm going to make this a simple, the simplest positive charge that I can come across. This proton is going to be at rest. I let it go, and it's going to accelerate because it's in an electromagnetic field. You got to keep this in the back of your head. We're thinking about potentials, but you can also look at it at the other way, that in terms of forces, it's going to experience a force of repulsion with these positive charges and attraction with those negative charges. So it's going to accelerate in this direction. And if I turn my head away and come back a couple seconds later, it's going to be down here traveling at some velocity final. It started at rest. It it ends at some final velocity. I can use my conservation laws now to figure out what was going on. My initial kinetic and potential energy is equal to my final kinetic and potential energy. My initial kinetic energy, by stipulation, it was at rest. I was holding it there and I let it go. So my initial kinetic energy is 0. The velocity initial was 0. I had some initial potential energy because I know that that's being converted into kinetic energy as it falls, quote unquote, through this potential difference. And in the end, it's going to have some final kinetic energy, and it could have some final potential energy. But what I've done here is simplified my life and just said that V, the potential is the 0 of the potential scale is 0 here, so that this term is going to fall off and become 0. This all simplifies down to QV initial, right? My initial electrostatic potential energy is equal to my final kinetic energy. In this process, all that potential energy that it had here is converted to all that kinetic energy that it has here. And again, doing this trick of just solving for velocity, right? What I'm doing is I'm solving for this guy right here, get it on the left-hand side of the equation, put everything else on the right-hand side of the equation, and then take the square root. Now, if I do everything in SI, my charge should be in coulombs, my mass should be in kilograms, my potential should be in volts. Here's the numbers for a proton. For now and forevermore, the mass of a proton is always this number, the charge is always this number. And we've set up a 10-volt potential difference between these parallel plates. If I put these numbers in, I can then very easily with my calculator just boop, 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 and I've got a number. This thing falling, this simple proton falling through 1-volt potential difference, something that you get in, your calculator battery, is going to accelerate that proton from 0 to 43,000 meters per second, right? So this is, one example of how to use this idea of potential. All we needed to know was the battery was 10 volts, and we could figure this out very quickly. And this is also how a huge swath of technology works, basically on this principle of accelerating charged particles. So this is how a linear accelerator works if you're talking about, particle research. It's also, for those of you that are going into the medical field, this is basically how you're going to create radioactive isotopes with a linear accelerator on a tabletop, so that you can use these as tracer elements in doing MRIs and PET scans and things like this. It's the basis of how televisions were devised, how oscilloscopes were created. It is still to this day the basis for how X-ray machines are operated. This simple idea of I put a charged particle in a potential difference and it accelerates is the basis of a huge amount of modern technology. And it really is, instead of calculating it in terms of electric fields and forces, we can do it just simply in terms of this potential difference. So typical voltages, I think I'm getting close to the end of the lecture. Typical voltages, if you do an EEG on someone's brain, these are in the microvolt. I remind you, this mu symbol is 10 to the minus 6. Cells, what we'll find, and I hope that Dawn has some nice examples for you guys of this. Cell membranes, a lot of the engine, the mechanisms of biological cells depends on the fact that the inside and the outside of the cell membrane has a potential difference, so that things will want to go in and out whether they're charged or not, or depending on whether they're positively or negatively charged. Those potential differences are on the level of 100 millivolts. Your typical toys, you know, and things that you have laying around the house are, you know, 10 volts. You stick your finger into the wall with a fork or something, that's 120 volts. Household electricity. Static electricity is actually quite large. The amount of it is quite large. The amount of charge that's moved when you actually, you know, you scrape your feet on the shag carpet, and then you go and you shock your little brother behind the ear. The voltages that you are generating in that process are huge. They're tens of thousands of volts, but the amount of charge that actually gets, you know, distributed from your finger to the back of someone's ear is fairly small. So even with this huge amount of potential difference, the charge transferred is kind of small. Transmission lines. So if you walk around your neighborhood and you look up and you see the power lines, they are typically transmitting power at huge voltages. This is supposed to be a capital M, a mega, 10 to the 6 in SI. So just typical sizes of these voltages. And I think the last thing that I'm going to introduce here today is the idea of an electron volt. So if we have an electron and it has a fundamental charge of negative 1.6 times 10 to the negative 19 coulombs, if you take an electron and you move it through a potential difference of 1 volt, it's going to gain a kinetic energy. So this is the opposite situation of what we just saw with the proton, because it's an opposite charge. It's repulsed by these negative charges. It's attracted to those positive charges. So it's going to want to go zoom and fly up to that positive charge. It gains kinetic energy in this situation because you'd have to do work to push it from this down to that. It's the opposite of what we just saw with the proton. The only reason it's the opposite is because the electron has a negative charge. It's the exact same magnitude of charge, but a negative value for that. If we look at the work that we'd have to do to do that, it's opposite to the gained kinetic energy that you would get if you change through that potential difference. I multiply these two numbers together, 1.6 times 10 to the negative 19 coulombs times a volt. In SI, remember, if I use SI going in, I'm going to get SI coming out. So coulombs is SI, volts is SI. I know that kinetic energy and potential energy is in joules, so I'm going to get joules. And this tells me that a joule is equal to a coulomb volt. Okay, this is new and weird and different. Another way of saying this is 1 volt is equal to a joule per coulomb. We'll come back to that, I promise. But what the main point of what I wanted to show here is we're defining, so this is the amount of energy that electron gains as it goes from here to there, as it falls through that potential difference. It's going to gain this 1.6 times 10 to the negative 19 joules. It's an absurdly small amount of energy on normal everyday scales. So what we need is something that makes sense on these tiny energy scales. We define something called an electron volt, which is 1.6 times 10 to the negative 19 joules. And this is the same idea as calling, 12 eggs a dozen, or 1 calorie is equal to 4.19 joules. It's just a redefining that kind of changes the scale just for convenience. And this is something, again, I don't need you to memorize this. This will be provided on tests and stuff. But just to know that an electron volt, an EV, is equal to some number of joules, in the same way that a calorie is equal to some number of joules. And you might see this, this energy unit coming up again and again. Okay, so that's actually my lecture for the day. I have we could try out some polling here, which is the equivalent of clickers in Zoom. I can pause here for questions because that's as much as we have. I can scroll back in the notes if you'd like me to. I'll address anything that you want, or let me give it 20 seconds. You guys decide, and if not, I'll take it in whatever direction feels natural. So while we're waiting, my kids really wanted me to do something for April Fool's Day. So I think this is creepy, but they gave me these. So what do you guys think of these? Is that working for you? Or I can hardly see very much on here, but they were very much made me promise that I would show you that. Okay, so April Fools, my eyes are weird today. Sorry. Anybody out there? All right, so let's okay, you should start the next. I should start the next lecture like that. So Marilyn says I should start the next lecture like that. Just pretend like there's nothing going on and just be like, all right, good morning, everybody. How are you doing today? We're going to talk about electrostatic potential energy and just see if anybody even comments on it. I thank you, Marilyn. Maybe we'll see if that happens. Let me try. I want to try this polling feature. Okay. Brandon says, yes, that would be great. So, let me see. Tell me, guys, if you can see a poll. I'm going to launch a poll. You guys are my early crew. So do you see a poll in front of you? So can you, So do me a favor and just choose, if you can do a poll, answer the first one, just choose A, and I'll come back to that some other time. I want to get to the second question if we can. Are you guys able to take a poll?
I can't see a poll.
You can't see a poll. Is that right? I don't see it.
Yeah, no poll is showing up.
Okay. Okay. Well, that answers my question. The poll is very happily landing on my desktop here, but it's not showing up for you. Thank you for letting me try. I'll just close that. That's an abject failure. So with that being said, do we have any questions?
It does look like one person got the poll.
I got the poll. Amelia Harridan got the poll. That is so weird. Why
It's Ben joining that let me take the poll.
It didn't let you take the poll?
No, it did, but I just joined the Zoom lecture, so I don't know if that affected it.
Okay. You know what? Maybe it's you just joined the Zoom lecture. Are you here for the 9 a.m.? Is that what's going on?
Yeah.
Maybe with the 9 a.m. I have something changed in the configuration so that it's set up properly. Thank you, Amelia, for letting me know. I still obviously need some help with getting this tech right, but hopefully by next time around we will have polling working again. Any other questions about electric potential or things of that nature? The question I wanted to ask you guys, and maybe you can start thinking about it, was, the participation is getting a little bit less in the morning at the 8 a.m. And I want to know if, would you guys be more comfortable joining the 9 a.m. or is this like the time of day that you can make it? I need a little bit of feedback there. If, for the people that are here, is this the time of day that you can do it? And then you're moving on to other things. So I'll try to launch that poll for real next time. And thank you for your patience. No, I have another class at 9. I can't do 9. I have other classes. Okay, that's thank you. I prefer this time. All right, we got a bunch of answers already that would be a problem. So I appreciate your rapid responses on that. Okay, everybody, I'll leave this open for another 2 minutes until the lecture is supposed to be done. Feel free to keep putting the comments in there or asking any other questions. And in a moment, I'll have to kick everybody out so I can start the new lecture. I hope you're all doing well out there, and thank you for joining this morning.